Hello students, today we will be discussing important topic of liquid solutions chapter, that is colligative properties. First, let's understand what is the meaning of colligative properties, which properties come under this category. See, colligative properties do not depend on the nature of solute but only depends on the number of solute particles relative to the total number of particles. Meaning, colligative properties, that means the properties which do not depend on the nature of the solute. Suppose if you take glucose added to the water in one beaker and sucrose, another substance, so nature is different from glucose. So, and it is added to the another beaker. So, two beakers are there. In one I have added the glucose substance, in another beaker I have added the sucrose substance. Two different substances. But if I add same number of moles, for example, if here I have added 1 mole of glucose and here I have added 1 mole of sucrose. If I add same number of solute particles, even though nature is different for the solutes, the property values will be same in one beaker, first beaker and second beaker. If such properties which do not depend on the nature of the solute but depends on the number of the solute particles, those are called colligative properties. We study 4 such properties in this chapter. One is relative lowering of vapor pressure, simply called RLVP. Now this relative lowering of vapor pressure value will be same if you add glucose to water or sucrose to water or urea to water. What is the nature of substance added does not matter. Only how much you have added only matters. If that is same, then automatically this value also will be same. Now let's see what is this relative lowering of vapor pressure. See, suppose if I take there is a beaker and there is a liquid, and let's say P0 is the vapor pressure of that pure liquid. P0 is the vapor pressure of the pure liquid pressure present in the beaker. Now I have added solute in the beaker. Let's say these are the solute particles present in the liquid solvent. Liquid solvent is there and in that some solute is added. Now here the pressure will not be P0 now because some solute is present which will affect the vapor pressure, and let's say here pressure is P and pure liquid pressure, vapor pressure is P0. Now this is a solution. Solution means what? Solute present along with solvent. Whereas first case is pure solvent. There is no solute here. So in pure solvent vapor pressure P0, in solution vapor pressure P. Now this P0 minus P is called lowering of vapor pressure. Lowering means decrease in the vapor pressure. How much vapor pressure has come down from P0 to P, that is lowering, divided by P0 denotes the relative lowering. Relative means compared to the original pressure, how much is lowered. That is what relative lowering of vapor pressure. Now this RLVP value is equal to what? Mole fraction of solute. This is called mole fraction of SU means solute. Mole fraction is denoted with the alphabet X. So XSU means mole fraction of solute. That means mole fraction of solute means what? Moles of solute divided by moles of solute plus moles of solvent. Solute plus solvent in the denominator. So how much you have added solute to the solvent, that only matters here. what substance you have added, glucose you have added or sucrose you have added, it does not matter here. How much you have added, how many moles you have added. If you have added same number of moles of solute, then this mole fraction value will be same for the two beakers, glucose beaker or sucrose beaker. Therefore, you will get the RLVP value also same. That is the meaning. So this is one colligative property. Let's go to the another colligative property, elevation of boiling point. See, I will discuss both elevation of boiling point and depression of freezing point together. These two are the two other important colligative properties. See, I will explain with a phase diagram. This is a phase diagram. This white color one is a white curves are the phase diagram of pure water. Pure water phase diagram is this. Suppose if I draw, look here. If I draw phase diagram of pure water, something like this it will come. Now, here solids will be there, here liquid, here gas. What is the meaning of this? See here, if any point you take here, at that particular pressure and particular temperature, substance will be in the solid state. Water will be in the solid state. If you take any point here, then it will be in the liquid state, substance, that is water here. If you take any point here, at that particular temperature, x-axis is temperature, y-axis is pressure. At that particular temperature and the pressure, substance, that is water, will be in the gaseous state. That is the meaning of phase diagram. Now, what is the meaning of this boundary? There is a boundary line is there here. What is the meaning of these boundaries? If any point you take on the boundary, then at that pressure and temperature, both liquid and solid, because it is boundary between both liquid and solid coexist in equilibrium. That means, in other words, it is the melting point or freezing point of the substance. Suppose if you take any point on right side boundary, any point you take on that curve, that point, since it is a boundary point between liquid and gas, it represents what? At that pressure and temperature, both liquid and gas coexist in equilibrium. That means it is the vaporization point. It is a vaporization scenario. Okay, now see, if you take this white curve, this is the pure water phase diagram. And if you take the yellow one is the solution phase diagram. That means if you add solute to the solvent, if you add, then the solvent's phase diagram will be differing slightly. See, this is the pure water phase diagram, pure solvent. This is the solute plus solvent. When you add solute to the solvent water, then water's phase diagram is this yellow curves, which is slightly below or behind the white phase diagram. Now, that's why we have written, see here, white one denotes pure water diagram, yellow one denotes solution diagram. Now here, if you see, y-axis is what? Atmospheric pressure, x-axis is what? Temperature. Now, what is the normal atmospheric pressure? 1 atm. So let's take the 1 atm horizontal line. Now it is touching this yellow line at this point, whereas white line at this point. Similarly, here if you see, white curve at this point, yellow curve at this point. Now, I already mentioned, if any point on this boundary, that is denoting the vaporization point or liquid gas equilibrium point. So, this point on the white line, white curve, denotes what? Since it is the boundary between liquid and gas, it is the vaporization. Now, when a liquid water is boiling into the gaseous water vapor, the temperature, corresponding temperature is denoted here as TB naught. See the white color letter here, TB naught. TB naught is the temperature here. Now, so this is the boiling point of the pure water. Now when you go to the solution, after adding solute to the liquid water, now it is solution, that is yellow curve. Now here if you see the boiling point, see now this is the new point here. At this temperature if you see, what is the temperature here? TB. Now TB is the boiling point of the water in case of solution after solute is added. Whereas TB naught is the boiling point of water when there is no solute, pure water is there. So this is the original boiling point of pure water. This is the boiling point of the water in the case of solution after solute added. Now if you see, initial value is small, final value is right side, means big. So boiling point is elevated. Boiling point is elevated. That's why we have written here elevated. Boiling point has increased. And if you see how much that increment in boiling point, elevation of boiling point, that is increment in boiling point, TB minus TB naught is how much? KB, which is a constant, boiling point elevation constant, into this small m means don't think that it is mass, it is the molality. Molality of the solute in the solution. So molality into Kb, Kb is some constant, will give us how much that elevation is happened. No matter which solute you have added to the solvent, if molality is same, then Kb into m will be same only. So can I say it is also a colligative property? Yes, because it does not depend on the nature of the solute. It depends only on the molality, means quantity of the solute. Similarly, if you see the left side, see this point is the boundary. I am taking the point on the white line boundary here. This point what denotes the freezing or melting related point. So pure water related temperature is Tf naught, which is the freezing point of pure water. In case of solution, go to the white line, yellow line. Corresponding temperature is denoted as Tf. Tf means what? Temperature or freezing point or melting point of the water in case of solution. In case of solution Tf, in case of pure liquid water Tf naught. So if you notice here, Tf naught to Tf, the value has become reduced. That means depression, decrease in freezing point took place here. In case of boiling point is elevated from the pure scenario to solution scenario, whereas in freezing case, freezing point means the temperature at which solvent liquid water freezes. That value has depressed or decreased from the pure water to the solution scenario. This is the case. And here depression of freezing point. Depression means what? Initially value is more, finally less. So we write it as Tf naught minus Tf. So this value will be Kf into molality. Again molality only m is. And Kf is again constant, but this time this is freezing point constant and into molality. So delta Tb is Kb into molality and delta Tf is Kf into molality. But that is elevation, this is depression of freezing point. Fourth colligative property is osmotic pressure. See, osmotic pressure is another colligative property. What does it mean? First, let's understand what is osmosis. Then we will see what is osmotic pressure. Now see, suppose there is a pure solvent one side and solution another side. If you connect them with a semi-permeable membrane, then the pure solvent flows from this side to the solution side through the semi-permeable membrane. This is called osmosis. And if you apply the pressure on the solution side, for example, if you apply some pressure on the solution side, then you are pressing, you are putting some pressure means you are pressing. Then what will happen? From solution side, flow will increase to the solvent side. Because of this, the osmosis will be reduced. Osmosis means flow of solvent from the pure solvent to the solution side. When you apply the pressure on the solution side, you are pushing the solvent to go to other side. So definitely the rate of flow of solvent, rate of osmosis will be reduced. And if you keep applying the pressure, increase the pressure so high, it is equal to the value of some pi. Okay, pi is not here 3.14. Pi is pi is denoted as osmotic pressure. So osmotic pressure, if you apply that much value, then what will happen? The osmosis which is happening from the pure solvent to the solution side completely comes to stop. There is no net flow of solvent. When the pressure is sufficient enough, which is equal to the osmotic pressure, then there is no osmosis takes place between the beakers. So what is osmotic pressure? See the definition. Extra applied pressure. Why it is written extra applied pressure? Already atmospheric pressure is acting upon two beakers. What is the extra pressure you are applying on the solution side? That is only called as osmotic pressure. The extra applied pressure on the solution side to stop osmosis is called osmotic pressure. To stop osmosis, you have to apply the pressure in such a way the osmosis should be stopped. Such pressure, extra pressure applied on solution is to be called as osmotic pressure. Now that is also another colligative property, and that is calculated using a formula CRT, where C is here, molarity here. It is not molality, it is molarity, moles per liter. And R is universal gas constant, and T is temperature in Kelvin. Temperature in Kelvin, remember that. Now here also, what substance you have added as a solute does not matter. How much you have added, what is the molarity, that only affects the value of osmotic pressure. Therefore, this is also another colligative property. Now, let's see one more important point, Van 't Hoff factor. Then we will see some problems, some applications on this osmotic, this colligative properties. See, Van 't Hoff factor. See, Van 't Hoff incorporated correction factor called I to take into account dissociation or association of solute after adding to solvent. See, when you add solute to the solvent, for example, glucose you have added to the solvent water, nothing happens. Glucose molecules remain as it is only. But if you add some solute to the solvent like NaCl you have added, before adding NaCl is 1 unit, but if you add to the water, then what will happen? This Na plus and Cl minus will separate from it. So 1 mole of NaCl if you add, after adding 1 mole of Na plus will come out, 1 mole of Cl minus. Total how many particles are there? 2 moles of particles are there. You think you have added 1 mole, but after that it has become 2 moles of solute particles. Whereas in case of glucose, if you add 1 mole, after addition also it remains as 1 mole only. So some solutes will undergo dissociation after addition to the solvent, whereas some solutes undergo association. This will affect the colligative property values. And previously when we see the formulas, this factor is not considered anywhere, dissociation or association. Van 't Hoff has done experiments and considered this phenomenon also, association, dissociation, and introduced one correction factor in every formula. that will take care of this association dissociation phenomenon. See, RLVP, relative lowering formula is what? Earlier we have seen mole fraction of solute. But Van 't Hoff has introduced the correction factor I. Delta TB, elevation of boiling. Now earlier we have seen KB into M, now I. Van 't Hoff factor. Again, depression of freezing point, Kf into M, I. Like that, again pi is equal to ICRT. If I is equal to 1, then all will be transforming into the previous formulas. Without correction factors, what we see, same formulas we will come out. If Van 't Hoff factor is 1. If it is not equal to 1, whatever will be the value, that will be the, whatever the actual colligative property value, this will give that value. How to get, next question arises, okay, how to get this Van 't Hoff factor value I? Now remember, Van 't Hoff factor I is calculated like this. Total number of moles of particles after dissociation or association, means after breaking, how many total moles are there in the beaker, in the solution, divided by number of moles of particles before association or dissociation. For example, if you take a solvent water and you have added 1 mole of NaCl, then what will happen after adding to NaCl? It breaks down into Na plus and Cl minus. Na plus also 1 mole, Cl minus also 1 mole. Now, if you have to find Van 't Hoff factor of NaCl, number of moles of particles after association or dissociation, whatever takes place in the beaker. Now here dissociation is taking place. Now after dissociation, how many total particles are present in the water, in the solvent? 1 plus 1. So Van 't Hoff factor is 1 mole of Na plus 1 mole of Cl minus divided by, before association or dissociation, how many are there? Before breaking down into a cation and anion, originally how many moles of solute is there? 1 mole is there. So 1 mole. So finally 1 plus 1, 2 moles. Initially 1 mole. So Van 't Hoff factor here will be 2. In this manner, we need to identify the Van 't Hoff factor. As a shortcut, you remember, mostly it will help in dissociation scenarios. Shortcut for Van 't Hoff factor I in case of dissociation. If dissociation is 100%, sometimes they don't mention how much percent dissociation is happening. We will assume then 100% and proceed. Then Van 't Hoff factor is number of ions. If dissociation is 100%, Van 't Hoff factor is number of ions. If dissociation is partial, sometimes they mention 80% dissociated, 50% dissociated. They will mention that. If that is partial, then Van 't Hoff factor is simply you apply this 1 plus number of ions in the solute, how many ions are present in the solute, minus 1 into alpha. For example, if you take Na2SO4, Na2SO4 has how many ions? 2 sodium ions, 1 sulfate ion, total 3 ions. So if they ask 100% dissociation, 100% dissociation, what is the Van 't Hoff factor? 100%, what is the Van 't Hoff factor? Just number of ions. That means how many ions are there? 2 sodium, 1 sulfate, total 3. So Van 't Hoff factor is simply 3. Suppose if they say in the question, Na2SO4 is only 80% dissociating. what is the Van 't Hoff factor? Then apply the second relation. What is that? 1 plus ions minus 1 into alpha. Ions is what? Here 1 plus ions is what? 3. 3 minus 1 is what? 2. So 2 alpha. What is alpha? 80% dissociation means alpha will be 0.8 degree of dissociation. So therefore 1 plus 2 into 0.8 is the Van 't Hoff factor here. Like this you have to calculate. If no dissociation or association happens, for example glucose, sucrose, urea, this kind of substances when you add to water, they don't undergo dissociation, they don't undergo association also, nothing happens to them. 1 mole if you add, they remain as 1 mole only. So in that case, Van 't Hoff factor will be 1. When Van 't Hoff factor is equal to 1, all the formulas, corrected formulas also become into the original formulas. If you take I value 1, all becomes into the previous original formulas without correction factor, whatever is there, that only we will get. Next, let's see a few problems on this. Find I value for the following. Now see, here they have given 80% dissociation. Means dissociation is not 100%. We have to understand that. So if partial dissociation is there, what is the formula? I is equal to 1 plus number of ions minus 1 into alpha. So here in K4FeCN6, how many ions are there? 4 potassium ions are there. 1 FeCN6 complex ion is there. So 4 potassium ions, 1 complex ion, total 5. So 1 plus 5 minus 1 into alpha is 80% means 0.8. So 1 plus 4 into alpha, 4 into 0.8 is the answer. Next, look at the second part of the question. Fe2SO4 thrice. Here they have not mentioned how much percentage it is dissociating. When they don't mention that, we will take 100% dissociation. Therefore, just answer Van 't Hoff factor is just number of ions only. How many ions are there in this Fe2SO4 thrice? There are 2 Fe plus 2, Fe plus 3 ions, 2 iron ions and 3 sulfate ions. 2 iron ions and 3 sulfate ions. Total 5. Therefore, answer will be simply 5. So like this you have to calculate in this. Next, freezing point is least for. Freezing point is least for which case? Now see, first let's see the formula of depression of freezing point once again. What is the formula? Delta TF, that means TF naught minus TF. That is what delta TF is equal to KF into molality. If you include correction factor also, always include correction factor only. If no dissociation association happens, Van 't Hoff factor will be 1. If something happens, it will take care of that change. So always you consider the Van 't Hoff factor in the colligative property formulas. So let's take Van 't Hoff factor also I. Now notice carefully here. This is the pure solvent freezing point. Freezing point of pure solvent. TF naught means. TF means what? It is the freezing point of solvent only, but in case of solution. When solute is added to solvent, in that solution, what is the new freezing point of the solvent there? That is what? TF. Now, when they ask freezing point is least for, they are talking about which value? This TF. So freezing point value. Now see, first let's take the, see if you see here, this is a solution containing solute. This is also a solute, NaCl containing solution, K2SO4 containing solution. These are the three solutions here. This is pure water. There is no solute here. It is pure solvent here. Now we know that compared to pure solvent, solution has freezing point less because depression of freezing point happens. So compared to pure water, boiling point of solution is elevated more, whereas freezing point of solution will be always depressed, means small, lesser than the pure water. So pure water will be highest among the four options, but they are asking the least. So forget about the fourth option. Now we have to compare first, second, third and select the least freezing point one. Now freezing point TF has a negative sign in front. See, there is a negative sign in front, the TF value. So if IKF molality value is big, right side quantity value is big, then because of minus sign here, TF value will be small. TF freezing point will be small here. So we understand that least freezing point we want means what? Because of minus sign, right side quantity has to be big. If I into molality value, if you check in the options and see where it is the biggest value, automatically freezing point, because of minus sign, I am repeating again, because of minus sign in front, freezing point value will be smallest. So let's check in the 1, 2, 3 options where this I into molality value is big. Okay, so first option let's take 0.1 molality urea. So urea has Van 't Hoff factor 1. So I into M value will be, Van 't Hoff factor is 1, molality is 0.1. Second option, 0.1 molality NaCl. Here if you calculate I into M, I is what for NaCl? NaCl 2 ions are there. 2 ions are there means Van 't Hoff factor also 2. So 2 into molality is 0.1. Third option, 0.1 molality K2SO4. So here also I into M is, I is what here? There are how many ions present? 2 potassiums, 1 sulfate, 3 ions. So 3 into 0.1 molality. Now, so if you see I into M, which is the biggest value? Here 0.1 is the I into M value, here 0.2, whereas here 0.3. 0.3 is biggest. So higher the IM value, higher the right side quantity, therefore lower or smallest the freezing point value, TF value. Therefore answer will be third one. So this is how you have to calculate the freezing point. Suppose in this question if they ask which of the following option has the highest freezing point, then answer will be water, pure water, because pure solvent has freezing point highest. Any solution will have freezing point depressed, means lesser than the pure water. So maximum if they ask in the question, answer would be water. Minimum if they ask, so among the solutions we checked and found the third option. Next, VP. VP means here vapor pressure is least for which option? Vapor pressure is least for which one? Now see, first let's write the relative lowering of vapor pressure formula. P naught minus P by P naught I into mole fraction of solute. Now look here, this P is the vapor pressure of solvent in solution. P naught is the pure water vapor pressure, P is the vapor pressure in case of solution. Now see, if you see all contain some solutes, so we are dealing with the solutions. Among the solutions, which one has the least vapor pressure, they are asking. Now see here, if P value is least, because of minus sign in front, I into X value should be highest, just like the previous problem. If P value has to be least, there is a minus sign in front, so negative effect will be there. So right side I into X value has to be highest. So in the options we have to check which of the four options have I Van't-Hoff factor into mole fraction highest value. If you see, they have given the molarity, not the mole fraction. Molarity they have given, and molarity value is same for all. So what I will assume here, if molarity is same for all, concentration molarity term is same, I would assume that even mole fraction also almost same for all. I don't calculate that value of mole fraction. I will take that also value will be same for all solutions here. So if mole fraction value is same, then can I say if mole fraction is same, then I would check instead of I into X, check only I value. If I value is maximum, automatically vapor pressure will be minimum because of minus sign in front of vapor pressure. Okay. Now, glucose. Glucose, what is the Van't-Hoff factor? We know glucose, urea, sucrose, they don't dissociate or associate. Van't-Hoff factor is 1. NaCl, Van't-Hoff factor is 2 because 2 ions it contains. BaCl2, 1 barium ion, 2 chlorine ions. So Van't-Hoff factor is number of ions 3. Here how many ions are there? 2 aluminum, 3 sulfate. Total 5 ions are there. Therefore Van't-Hoff factor 5. So among these, already mole fraction values I assume to be same because molarity is same. And Van't-Hoff factors, if you see, which one has highest Van't-Hoff factor? Fourth option. Highest Van't-Hoff factor means automatically right side quantity will be highest, vapor pressure will be lowest, smallest. So this is the right option. Boiling point of 1 molal means molality. Molality NaCl is 373.936. This is the boiling point. Boiling point of what? Boiling point of water only, solvent only, but in case of solution where NaCl is already present in it. Degree of ionization of NaCl is what? Alpha they are asking, degree of ionization. Kb of water is given and we have to select the right option. See, we know the elevation of boiling point formula. Tb minus Tb naught is this, I into Kb into molality. What is Tb? Boiling point of water in solvent in case of solution. That is only given in the question. This is in case of solution only boiling point. Take that. And Tb is what? Tb naught is what? Tb naught is the boiling point of pure water, pure solvent. Pure solvent water we know 100 degrees centigrade means 373 Kelvin. So take that. Now, since we need to calculate the degree of ionization, that means alpha, so we will take Van't-Hoff factor like this for NaCl. NaCl has 2 ions. So NaCl has 2 ions means, can I take Van 't Hoff factor as 1 plus number of ions minus 1 into alpha. Alpha is degree of ionization. How much it comes out to be? 1 plus 1 alpha. 1 plus 1 alpha. This is Van 't Hoff factor into Kb. Kb is also given in the question, 0.52 into molality. Molality is given as how much in the question? 1 molality. Substitute that. Then you simplify this. This comes out to be left side 0.936 and 0.52 you bring to the denominator. Now this one calculation also, and don't consume more time in your calculations, because in exam time is also important. So go for the approximations. Say 0.93, 0.52. This one I will take approximately 0.9 by 0.5. Because 0.93, 0.52 I will take it as 0.9 by 0.5, because similar second decimal place is similar only in both, 3, 2 almost close. Therefore I will take like this. 0.5 means what? 1 by 2. So this can be written as 0.9 into 2, around 1.8 you will get. So 1 plus alpha is equal to 1.8 means alpha is equal to how much? Around 0.8. So see which option has that 0.8. Like that, if you take closest approximations and proceed, it will save you a lot of time, which will help in solving other questions and get more marks. That's it. I hope this discussion is helpful to you. Okay. Always remember, whenever you are using colligative property formula, always use the correction factor I also. There are only 4 formulas, one for the relative lowering, second for the elimination of boiling, depression of freezing, and osmotic. In 4, take Van 't Hoff factor and remember how to find the Van 't Hoff factor. This is also more important, and just apply the formula and substitute, you will get the answers. Practice problems on this concept. First go through this all discussion once again and practice these questions. Then only you will get more confidence. I hope this will help you and get good marks in exam. Thank you.